Okay, so pass by value, pass by reference. How did any of this just work? So the overview. The way we treat primitive and complex data types have different behaviors depending on when they're passed around and when they're evaluated. Real quickly, what are some of the complex data types? Arrays, objects are the main ones that we're going to see this with, functions as well. And we'll cover that more tomorrow with higher order functions when we pass functions around. Today we're just going to do objects and arrays, but they're all complex and they do have this ability to pass by reference, which means point to a specific place in memory so that various variables can all access the same bit of data. So this is most evident during variable assignment and when we pass values into functions like we just saw, passing person2 in, that then becomes person just to that function. We'll also go over how the equality operators work when trying to compare complex data types and how pass by value, pass by reference plays into that. And at the end, we'll talk a little bit about immutability, which is this idea of, hey, give me an object or an array that looks exactly like the other one, but it should be different. It should be a different spot in memory so I can change this new array without affecting the original one. And any function that basically creates a clone and looks similar but won't update both of them is an immutable function. And slice is an example of that. If you remember, if we call an array with slice and no parameter, we get back an array that looks exactly the same as the other one, but it's an immutable copy and they're actually different places in memory, and mutating one won't change the other. So visually, here are the primitive and complex types. Arrays are of type object, so they group those two together on this slide. Don't worry about ES6 symbols. The rest of the primitive values you know. So primitive values will all be passed by value, and these complex types will all be passed by reference. So what does that mean? What does that look like? Strings are primitive values. So here we have two variables. And the first one is British city, which we're setting equal to the string value York. Now on line 3, we create new space in memory called American city and set that equal to British city, which means at this point in time, American city needs to resolve to a single value. So to do that, we look up what British city is in scope or in memory. And we'll see that at that point in time, British city was equal to the string value York. So American city will also be equal to the string value York. But each of these variables just points to a string value. They're not pointing to the same place, which means if we change one of them, we won't see the reflected change. So when we first log out down here on line 5, we say, okay, let's reassign American city. American city should now be equal to whatever this entire expression resolves to. So we take the string new with the space, and we say, what is the current value of American city? And in scope, we would see that American city was last evaluated over here and was the value York. So we plug in the string value York. New plus York now becomes the string New York. So this is a single value over here. And we say, okay, American city is now equal to New York. And it overwrites whatever it used to be. So down here, when we log out British city, is British city changed? What is British city? Yeah, British city last got touched on line 2, and it got told that it's the string value York. Literally the value York. It doesn't get affected by anything we do later on. What about American city? What is American city now? Yep. Arrays are complex values. So we do the same thing here. We create two variables where British city is equal to the array with the string value York on the 0th index. Then we say American city is equal to British city. This is going to operate a little differently. So we then unshift new off of what is known as American city. Now when I go to log out British city, what do we think we're going to see? I'm sorry? So we didn't touch British City, but we see that it shows the effects of that unshift. And that's because when we take an array or a complex data type, we say, hey, American City, you're now equal to British City, and British City was a reference to a spot in memory that evaluated to an array with the string value York inside of it. So we say American City, you're now pointing to that same place as British City. We're going to visualize this in a second. These are just like quick overviews. So then on line 5, we say, go to wherever American City is and unshift. And American City was pointing to a spot, like a memory spot in memory, that was where this array was. And we touch that array and we throw in the new string new. Later on, both of these are still pointing to the same spot in memory where that array actually lives. And so when we log them out, they both go to the same memory address and log out the same values. Do you have quick questions there before we dive in depth on how that worked? Yes,
so
Sean.
Any method to that array?
I'm sorry?
If you utilize any method in that scenario where the two arrays are not equal to each other, so they're pointing in the same place, anything you did to that array with a method would show up on both arrays.
Yes. Yeah. So we could have wrote 10 more variables here that we could have said, hey, South American City is equal to American City.
But it's really just one array. It's not two arrays.
Yes. So one array exists in memory, and each of these variables actually resolves to a memory address. They point to a place. So with string values, with primitive variables, they point to a specific value that only they touch and only they know. With complex data types, they actually point to a spot in memory, and you can have multiple variables pointing to that same spot in memory. So a change on that memory address will be reflected by any variable that also is holding a reference to that spot in memory. Danielle.
I don't know if this is backtracking or related, but can you explain the relationship between primitive and complex data and then also immutable and mutable data? Like, are those, I'm a little bit confused about that.
So what's the question about primitive versus complex?
Like, is that all, like, is immutable and mutable data, like, is that related to primitive and complex data types, or is that different?
Okay, so immutability and mutability is basically this idea of, are we going to actually change a thing in memory, or is it immutable, which means that we're going to instead basically clone it, put it in a new spot in memory, and only modify that. So immutability and mutability don't refer directly to the data types, but rather the function that touches them. So in the case of unshift, it doesn't return us really anything useful. It returns like the new length of the array. That's a dead giveaway that that's a mutable function. It's a function that's going to go to that piece of data in memory and actually change it. And that change in data will be reflected on any variables that now point to that same memory address. So we'll cover that again at the end, but do we think push is mutable or immutable? Mutable. Push is going to change anything that has a reference to that array, because wherever that array lives in memory, it's actually adding something into that array. What about slice? Immutable. So anytime a function returns you a new array, that's also a dead giveaway that, hey, this is an immutable function, and I'm giving you a new array to reflect the changes you wanted, but the one you told me to call slice on is unchanged. Does that answer your question?
Yeah.
Jimmy.
Just to make sure, if it's in a function though, it wouldn't change it, would it?
It depends what you do to it inside of that function.
Okay. Like if American City was in a function that says like it's equal to city, would it change it?
So you mean like the variable American City only exists in the scope of that function? So that variable only exists inside of that scope, but that variable is resolving to the same point in memory. And that's demonstrated in the first example we did. Person 1 lived on the global scope, but person 1 was pointing to memory address 1. Bear with me on the memory address. But inside that function, we then say, hey, make this new variable called person, and that's equal to whatever person 1 was equal to. And person 1 was equal to a memory address 1. So inside, person is now pointing at memory address 1. We can only use the person variable inside of that function because that's where it was defined, but it will change the data that existed there. Any other questions?
I guess with splice, so is that why there was that example where you would use splice to basically copy it by doing like 1, 0, and then you know.
Okay, so slice or splice?
I thought it was splice.
Okay, so slice is the immutable one that will give you a new copy. Splice was used to actually throw a value inside and to chop off other values.
Right, but if you, what was the one where if you did 1, 0, and you could add names to it?
That was splice.
Sorry, yeah, I'm thinking of slice. Never mind, we already talked about that.
Yeah, so slice will just give you a copy reflecting whatever changes you wanted. If we call slice with no parameters, it basically says, hey, take me from the start to the end of that array and give me back a new array that has the values that were in the one we just specified. Splice is the one that actually can delete stuff and throw new things inside of it, and it's mutable. And for that reason, splice is a little trickier to wrap your head around, and you can code yourself into problems, and that's why splice isn't used too often. It's generally easiest for us to use immutable functions. So why do primitive values and complex values behave differently? You'll be able to answer that at the end of this lesson. So when you assign a primitive value to a variable, the variable stores a copy of that value, whatever it evaluated to at that point in time. So in this case, we define a variable called first, and we put that on the global scope out here. So that happens as soon as we say let. Then we assign it. And we say, hey, this is equal to the value 20. So on scope, we now have this. Basically, you can look up the variable on scope first, and it will tell you that it's equal to 20. Now on line 5, we say, hey, go find whatever is called first. I don't care what it used to be. It's now equal to 30. And that 20 is completely overwritten. If we go look up first on any line after this, we'll get the value 30.
Even though there's like no command in front of that?
Yeah, so that's the assignment operator there is what's causing this to happen. And that's just the difference between how primitive and complex data types are assigned to a variable. So then second, we do the same thing. We throw second on the scope and just shorthand second is equal to 30. Now on line 8, we say, hey, go find wherever second is in scope and increment that value by 1. So we come in here and it changes to 31. So if we look up second after this, it will always give us back the value 31. So if we log out first, it says, okay, go find first on the scope and give me the value, and that's 30. And we log out second, same thing, 30 and 31. So what if I said console log third? What would it log out? Undefined, yeah, our scope only has first and second on there. So third doesn't exist, it's not defined, it has no value, it's undefined. Okay, in this case, we can see a little bit what the difference is between reassigning primitive values to another variable that was a primitive value. In this case, we have first on the scope equal to 20. When we go look up, here we're saying define second, so we have that sitting right here. We haven't solved this right side yet, so there's nothing there. Now we need to solve this right side of the expression. We say, hey, it's equal to whatever first is. So it looks in scope, it finds first, and first is equal to the value 20. So this 20 is what we take. So first and second are both equal to 20, but they're different in scope. They're both equal to the value 20, but it's not the same 20. So changing second down here won't affect first. What's happening here is we're saying go find second in memory. We find it. It says whatever that is, increment it by 1. First is unaffected. So when we log out first, we look to the scope, we find it on the scope, and it's the value 20. So 20 gets plugged in right here on 6. We evaluated first to 20, and that's what goes to console log is 20. It doesn't care about the variable. It just gets that value 20. And when we log out second, same thing, except we plug in the value 21. With me so far? When you assign a complex value to a variable, the variable doesn't store a copy of the value. Instead, it's going to store a memory address. So instead, the variable stores a reference in memory, and the reference points to where that complex piece of data actually lies inside of the computer. So in this case, as soon as we come here, we define first. As soon as we see this bracket, JavaScript is coded to know how to create an array and what to do. And when it does that, it says, okay, I need to make some space for this array. And we're going to go to the first available spot in memory, which we can call 0x1 or 0x00000001. Basically 8 bits in a row will probably be the first memory address that's available. So we make some space over there to equal this array. This is going to hold the array. And now over here we say, give me the 0th index, give me the first index, and those should have 10 and 20 inside of it. You able to see this?
Yeah.
And so now over here, now that we've created this, JavaScript gives us back the memory address of where this thing actually lies. So it says first is now pointing at memory address 1. So now on line 8, when we want to execute this, before we even come over here, it says, okay, I need to find first. I look up on my scope, I find that we do have a variable called first, and it's pointing to 0, 1. I find that in memory, and the code knows, okay, this is the thing that I want to do stuff with. And then over here, it does have the push method because it's an array. So JavaScript knows how to handle that. And it takes in the value 30, and it updates this memory address. So if we log first out again on the next line, first, the variable is still pointing to the same spot in memory. And when that gets evaluated to say, what is first right now, we will find this in memory and log this out. Does that make sense? So, new example. In this case, are first and second the same?
No.
Why?
They both get it. They're all reference memory.
Yeah, so both times we create this array, we're telling JavaScript, hey, go make some space to create those arrays. And so even though they look similar, they're pointing to different spots in memory. And as we'll see later, equality on complex data type says, hey, are these pointing to the same place in memory? So first and second right now are not equal. They're both their own arrays in memory. And so since they reference different arrays, pushing a value into the second will not affect the array referenced by the first. We're going to look up second on scope. We're going to go to memory address 2, and we're going to push in the value 30 into that second array. Does that make sense? And so when we log out first, we go on the scope, we find that first is currently pointing to memory address 1. We look that up in memory, and that's this array that only has 10 and 20 in it, whereas second has 10, 20, and 30. I didn't draw that one out, but we now have this beautiful diagram in the bottom right. Still with me? Okay, so what's going on in this example? we create the array in memory space 1 with the values 10 and 20 inside of it. And we say, hey, second is now equal to first. So when we have this assignment operator, we need to complete this expression and evaluate it to a single term. So we look up first on memory. And first in scope is basically pointing to 0, 1. So we say second is now equal to whatever first was, which is that memory address, 0x01. So that's what happens right here when we create space in the scope for the variable we know as second. So now when we say, hey, go to second and push in 30, we look up on scope, we see its memory address 1. We go over there and we change it to put in the value 30 at the end. And if I log out first, what will I see? Exactly, because when we go to log out first, it says, okay, where are we looking? We look for first, it's memory address 1. Memory address 1 now looks like this at this point in time. And that's what will be sent to the console to log out. Second is also pointing to the same spot in memory, and they'll look exactly the same. So quick question, are those equal? If we did first equal second, what do you think it will say? True. And so how that works is it looks up in scope and it sees, yes, 0x01 does equal 0x01.
So does this mean that the one before, when second was, it had its own array, but it was technically the same? If he did the Boolean, it would return false?
Correct. Because the actual values of the first and second array, in that case, second would have been pointing to memory address 2, which was over here and looked, even though it looks similar, that's not how we check equality on arrays. We want to know if they're pointing to the same spot in memory. Sean.
You did second equals, like let second equal first dot push 30.
Okay.
Would that create a new array, or would it just make both of them?
Okay, so that's the order of operations coming into play. So if we said var first equals this with an array like that, and we said var second is equal to first dot push 20, and we log out first, and we log out second, you want to know what second would look like right now.
Yeah.
Okay.
I know it looked like 10, but I think it looked like 1020, but I want to know if they're still pointing, if first also becomes 1020.
So the order of operations here says, okay, we made first, it looks like that, but just a 10 inside of it. Now we're making some space for second. Before we can decide what second is, we need to evaluate all of the code that's on this side of the equal sign. We could have 20 methods in a row if we got into method chaining, but basically we could have 10 plus 10 plus 10 plus 100 plus whatever. It can go all the way down the page. We can't solve what second is until we evaluate the entire expression up until that semicolon. So in this case, to start evaluating this code, we start from the left and we go to the right. And we say find the thing first, which is an array with 10 in it, and now access the key, push, which is a method. It's a function that JavaScript gave us, and it knows what to do. And it pushes to execute this method. It will push 20 into first. And so first will look like this, which means we've done this bit of code. But what does the push method return? So the push method returns the length, the updated length of the existing array. So once we do the actual push, this whole thing can now resolve to whatever the push method returned, which was basically 2. And so over here we say second is now equal to 2. And when we log out second, we find the value 2.
Okay.
If we log out first, what would we see right now? Oh, it's up there. because first is still pointing to memory address 1, and push modified that spot in memory because push is a mutable or immutable function. Mutable. It mutated the data. It mutated what existed at the memory address that this keyword referenced inside of it. Bunch of stuff coming together right there.
Can you give an example of immutable?
Yes. So if we said second is equal to first dot slice, and then we said second dot push 20. What do we think first and second will look like in this case? Exactly. So what happens is to do first dot slice, that method is basically under the hood, it's going to create a new array. It's then going to loop over first, take all of the values from first, and put them in that new array. Then it's going to spit back that new array at a new memory address, and that would look like this. So it found this. This is what this keyword referred to. It was this array in memory. It made a new spot in memory for a new array. It looked at this, and it copied each value down. And then it said, okay, I'm giving you this memory address back. So second is now equal to whatever is at memory address 2. Then on line 26, we go look at second again, which is pointing at memory address 2. We push 20 into it, and when we log that out, we go on scope, we find out what they're currently evaluating to. First is whatever at spot 1. Second is whatever at spot 2. And second is where the push method mutated it. Where slice was an immutable copy of what was at memory address 1. Make sense? Cool, those are great questions. We did this one, right? Second is equal to whatever first is referring to. Second, we push in 30 because they were referring to the same spot. When we log out first and we log out second, they're both 10, 20, 30. So first is equal to 10, an array with 10 and 20 in it. Oh, we just covered this. What will second look like? Yeah, this was the example that we just asked about before we saw it. Great questions. Okay, so passing primitive values. Again, we can return to this. We're creating some space in memory called mynum, and it's equal to the value 10. Then on line 3, we're creating some space in memory for a function called adds20. So we've got mynum, and that's equal to the value 10, right here, it ends there. Then on line 3, JavaScript knows how to handle this function keyword. It says, okay, so I need to add to the scope adds20, and I need to go define a spot in memory for that code to live. So you can imagine that at memory address 1 is this function that looks like this. That's where that code now lives. So adds20 points to a spot in memory where code, I don't know how to draw code, but it lives right there. And so that's what's going to be key to the next 2 days of lecture, is that we can pass functions around. And that's really unique to JavaScript and allows us to do really cool things. So then on line 8, we're saying, get me some space for returned num. So this is pointing to memory address 1. And now we're saying, get me some space for return num. So it makes some space, but it can't satisfy this yet until we evaluate all of this on the right side. So what this says is return num is equal to whatever adds20 resolves to when we pass in whatever mynum currently is. So first we have to look, before we even jump into the code, we need to figure out what to give adds20. So we look up mynum, we find it that it's 10, and we plug 10 into here. Now we can evaluate adds20. And so when we hop into adds20, we create a new functional scope. So this scope is what's going to be on this call to adds 20. And it's basically one layer deeper than scope. So while we're inside of adds 20, we say we need a variable called num. And because we invoked it with my num, which was equal to 10, inside of this functional scope, we say num is known as 10. So then we say num plus or equal to 20. So we look up num, we look in our deepest scope, which is functional scope, we find 10. We increase it to 30. And now on line 5, we return num, which is currently 30. So this over here evaluates to 30. And as soon as we hit the end over here, JavaScript has what's called garbage collection, where it says, okay, you can never see this again because your code ended. I know you can't see it. That scope is gone. It deletes it. It cleans up your memory. That's something that we don't have to do, but in other languages like C or C++, you actually have to clean up the memory yourself. And so that's another reason JavaScript is great. So that evaluated to 30, and as soon as the 30 got spit back over here, this cleaned up its own scope. And we now know that return num is equal to the value 30. This num out here is completely unchanged.
So you can also log num outside the function scope, it wouldn't work anyway.
Yeah, so this is our entire scope right now. If we go to look up num, it's not there, so it would be undefined.
That is why we use I all the time, because I exists only inside the loop.
Yeah, so I exists only inside of that loop. And basically, there's a curly brace there. So on each iteration, I is defined again. As soon as you hit the bottom, it deletes the old I, and then it makes a new one on a new scope. Exactly. Yes.
So my num in the scope and return num, they equal an address on memory, and that address equals 10 and 30. Correct? Or
Don't think that deep. Under the hood, it might work a little bit like that. But spotting memory is the scope. And these just evaluate literally to the value 10 and 30.
right.
Complex data types, the variables that hold them will evaluate to a pointer, that point all the way over here. But so yes, anything that's a primitive data type, it gets evaluated right there at that spot, and it won't touch whatever it originally came from. Okay, so we create some space in memory for an array that's going to hold the value 10. We create some space in memory for pushes 20. And now pushes 20 and my array both are references to where the code lives for that function and where that actual array lives in memory. Does that make sense? Then on line 8, we now make some space for return num again on the scope, and we say we're going to set this equal to whatever I get back from calling pushes 20 with whatever my array currently is. Now my array is a reference in scope to a memory address where this piece of data actually lives. And so now in here, we create a new functional scope. And in here we say, hey, give me a variable called array that is equal to whatever this was. This was equal to the memory address of this. So this is now pointing up here as well, wherever that exists in memory. So inside of this function, if we push 20 into this thing and we return it back, we now return the memory address of where that array was, and that is also equal to returned array. So returned array and my array are pointing to the same place in memory. That one was a little deeper. Do you want that on the board? Or do we know what these are going to log out? Okay, yeah, might as well. Okay, so as soon as we construct that array, we create a space in memory to hold whatever the instructions were that you gave it. JavaScript knows how to build this array and store a copy of the value 10. Then we do the same thing with pushes 20. It's complex, so that code lives somewhere else in memory. That way we can refer to it later. Now on line 8, we say, hey, give me some space for returned array. But we don't know what this is equal to yet. We need to solve whatever this whole expression is to the right up until the semicolon. And to do that, we follow PEMDAS, which means we have to hop in the parentheses first and work our way from the inner to outer, and we prefer to go from left to right. So in this case, before we can even execute pushes 20, we need to figure out what my array is. So we look up on scope, and we see that my array is currently pointing in memory to memory address 1. So we have memory address 1 kind of sitting right here. And as soon as we hop inside of pushes 20, so here's the pushes 20 scope, it says, give me some space for what I'm going to call array. And so in here, we create space for what it knows as array. And we say that's equal to whatever you gave me over here, which was memory address 1 over here. So array is memory address 1. So this is basically pointing over here. This is also pointing over here. Does that make sense so far? So on line 4, we say, hey, go to whatever array is. And in this case, we're going to look at our innermost scope first. And so we say, does array exist inside pushes 20? It does. What is it? It's pointing to this thing over here. Go to that thing and push in the value 20. And it does that on line 4. What does line 4 evaluate to? Trick question. Why 2? Yeah, so push returns the array of this that it just mutated. So in this case, push pushed in the value 20, and it evaluated that memory address has a length of 2. So that's actually, 2 comes and sits here on this line, and we don't do anything with it, but that does happen. We move on to line 5, where we say, hey, return whatever array is. We find array on the functional scope, and we return this memory address. So returned array is also equal to 0x01. So now my array and returned array are pointing over here. We're done with pushes 20. So that variable array, it disappears. But it was just a pointer. So it's completely gone, but the array at memory address 1 is still there. So returned array is now equal to whatever's at memory address 1. It's a pointer to that memory address. So when we log out my array and returned array, they both point to the same place. And it's going to look exactly the same when we log it out. Which means if I say my array triple equals returned array, what will that evaluate to? Exactly. So the equality operator, pass by a value, pass by reference. Did that one make sense? We've got nested scopes in there. We're passing references. And we saw how the right-hand side of assignments need to evaluate to a single value before we can decide what that variable now is. No questions, right? Cool. Okay, so in this case, we create 2 new arrays, array 1 and array 2. JavaScript knows that when it sees the brackets, it needs to make some space. Sorry, my handwriting is terrible. It creates 2 arrays in memory at memory address 1 and 2. And array 1 is the first one, and array 2 is the second. So when we go to, we're on the wrong slide. When we go to use the triple equal sign, JavaScript isn't going to do any crazy coercion. It's going to say, are these 2 things exactly the same? And in this case, to compare arrays, it wants to compare the memory addresses. So array 1 is pointing to memory address 1, and array 2 is pointing to memory address 2. Those are different memory addresses, even though the values at the memory addresses look the same. These variables are not the same, and this logs out false. Yes, Amani.
This may be a trick question, but what if you did double equals instead?
That's a good question, but in this case, it would still be false. Because they're both arrays, and arrays still they'll use the array versus array rule, which will return false because they're different memory addresses. Stuff can get really wonky if you start to see, hey, does an array equal a number? It's going to do some crazy unknown rule to determine if those two are the same. Probably not usually the same, but it can lead to some really strange bugs, which is why it's always safer to use the triple equals unless you have a set reason for doing so. But JavaScript does have a set of 36 rules that when you use only two equal signs, it has some method it uses to determine how to tell if those things are equal if they're of different types. If they're the same data type, there's no difference between the two and triple equals. So an array compared to an array, whether it's 2 or 3 equals, if it's not the same memory address, it's always false.
Did I
Norca.
say JavaScript
Oh.
has 36 rules?
Yes, I believe that was a number I saw on the slide a few weeks ago, but if we type in coercion rules, we can find it on MDM. It was in like one of the first slides of the class. I can link it again in Slack if you can't find it. But we don't actually need to look at it and memorize all of them because there's no good reason to ever compare an array with a number. You can compare an array's length with a number, but there's no reason to say, hey, is my array of possibly a string and then an object and a number equal to the number 100? That doesn't make any sense logically. You don't really have to know what it's going to do under the hood. So yeah, there's probably only a few of them that we have to know, which is like what happens if we compare a string to a number. If I say, does quote 100 double equal the integer 100? What does it do? Why? What does it do? Yes, exactly. In that case, when we compare a string and a number, JavaScript says, well, it's easier for me to convert the number into a string and then tell if these things are equal. So it will basically just put quotes around the integer, and if that now equals our quote 100, then it will say yes if we use double equal sign. What if we said triple equal sign, quote 100 equals integer 100? False. It says, are these exactly the same value and the same data type? And right off the bat, we've got a string, we've got an integer. It doesn't try to guess for us, it's false. So there's only a few that we ever really need to use, and most often it's numbers and strings. There's no real reason to compare these things with two equal signs. Norca.
So what if I want to compare the array with another array? Because I want to see if they have the same values inside. How do I do it?
Yeah, that might have been one of the workshop problems earlier this week. But yeah, basically you have to come up with that logic. And so we have to decide how to tell if those are equal. And so your definition, your rules were if each value is the same. So at the same index, or just that they hold the same values and the same amount of values. Yeah. Okay, so if you want to do the same index, pretty much you would set up a loop, and on each iteration of the loop, you would check both indices of those arrays. And if they're not strictly equal, you return false. If they are, if the first array, index 0, is the same as array 1 at index 0, do you return? I mean, do you return? These things have a length of 5. As soon as you see the first value, if they're both true, you can't return yet because we haven't checked the entire array. And so that was a trap that some teams fell into, was that they're like, okay, if they're equal, I'm going to return true. If they're not, I'm going to return false. And basically on the first iteration of your loop, you coded it that no matter what, you're returning. And even if we return in a for loop, it ends that function. So in this case, we said we want to know if they have exactly the same values all the way through. We can't return true unless we've gone through every single index. So that's just a logic trap. Okay, so over here we have array 1. We make some space in memory. It holds the values 1, 2, 3. Then we have array 2, and we say that's equal to whatever array 1 is. What is array 1 right now? The variable itself, what is it? When I plug it in on line 4. The variable itself is a pointer. Array 1 is pointing somewhere in memory. to memory address 1. So we say array 2 is now also pointing to the same place. So now when we go to log out array 1 and array 2, we see that they're literally the same memory address. And this is true. Trick question, but you had the right idea. Array 1 is 10, 20, 30. But just how this works under the hood is that we're giving them references. Okay, so we covered this a little bit before as well. We showed earlier that slice creates a copy of an array. But this is kind of tricky. So array 1, we define it. In memory, it says, okay, I need to go create an array. And so it does this. And it says, I have to evaluate each of these terms to a single value. So this 0th index is the value 1. That's easy. But when we come to the second index, does anybody have any idea what's going to happen? Yeah. So this array constructor is going to make a new spot in memory. So we're not done filling this in. But we have to create a new spot in memory called memory address 2. And over here, what is memory address 2 going to look like? In an array, right? So now we've solved what this second term was. We evaluated it to a single thing, which is this memory address. So array 1 is holding a reference in its first index. And that's a reference to down here. So now we come and we do array 2 slice. So we say array 2, we need some space. And lastly, we got memory address here. So we say array 2, we need some space. I don't know what it is yet. I need to solve this entire thing. I need to find array 1, which is at memory address 1. Okay, so I'm working off of this. It says use its slice method with no parameters and give me the result of that. So what slice does is it says, okay, I need to make a new array. And so this is going to be memory address 3. And it says I need to take each value that's in here and bring it down. So we take this 1. And what happens over here?
Still pointing at 2.
Exactly. That's the trick here. Slice is only giving us an immutable copy of the first layer. So we say this was a value, it was value 1. This was a value, it says memory address. I'm just going to copy that. I'm just going to steal that. I'm going to do the same exact thing and put it down here. So slice then returns this new array to us. But both of these arrays are still pointing to the same inner array. So this returns memory address 3, and we set that equal to array 2. So now when we log out array 2, what do we see? Same thing, yeah, we look up memory address 3, we find an array, we find value 1, we find a reference to another array, so we look at memory address 2, and then we log out an array with 2 and 3 inside of it. One sec. So on line 7, does array 1 strictly equal array 2? Why?
These are 2 different spots in memory.
Exactly, one is memory address 1 and the other is memory address 3.
And so that 7 wouldn't change, obviously, if you were somehow get into like memory 2 and change that.
One more time?
So let's say if you were able to get into memory 2 and change it to like 2, 3, 4. So that basically changes both of them when if you do console log array 1, console log array 2, they still look like they have the same values.
Yeah, so
changes both of them, even though they're in 2 different spots in memory because they're both calling back to that same one.
exactly. So if we have basically array 2 and we want to access the first index here, this part of the expression looks at memory address 3, and it resolves to this, memory address 2. this is this array. So now we do have access to the push function of that array. And we can push in value 4. So that would go over here and change this. Which means if we now log out the first index of array 1, what would we see?
1 array 2, 3, 4.
Exactly.
So you even if you use slice and basically make a copy, you're still not free of changing them if there's an array.
If there's any nested object or nested array, slice isn't going to make copies of that for us. So that might actually be a workshop problem. Basically, make a copy every time you find a complex data type called a deep clone. However, that's what's great about JavaScript and NPM is basically there's this whole world of libraries that people have just written all these functions that programmers need all the time. So a popular one is called Lodash, and Lodash has a deep clone on it. So instead of worrying about this with slice, you could import Lodash and call Lodash deep clone of array 1. And what we get back would basically clone the first array. Then when this sees that it needs this, it will make a new spot in memory to clone this one as well. And this would now point down here instead of up here. And so that's really important because when we get a lot of data out of a database, sometimes we do want to make copies, and we want those copies to totally not interact with each other. So if we had an object of friends, and each friend then had an array of their friends, and we copied the whole social network, we don't want to access the first friend and then change their friends and update that on the other copy of the social network. If that makes sense, I know that it's a lot, and I don't have the visual because we're going really late right now. So arrays and slice. If an array has a complex value as an element, only the reference to that complex value is copied into the new array. That's why we say slice makes a shallow copy. It didn't go and copy every other array that existed in memory address 1. And they just did this example we just did on the board. So to check that, we now log out array 1, the first index, is it equal to array 2? Yeah, so this is before we just made that example. Yeah, it was what was on the board 2 minutes ago. Basically, this one was still pointing up here. So when we only did a slice.
Oh, because it's array 1, 1. Yeah.
Yeah.
So yeah.
When we only did a slice before of memory address 1, memory address 3 and 1 at the first index still pointed to that inner array at address 2. So if we access that array from both of them, we're both getting a reference to memory 2. And so it's true. All right, recap. Primitive versus complex types. Primitive are passed by, and complex data types are passed by. What's a reference? Yeah, it's a pointer to somewhere in memory where that one piece of the complex data type actually exists. And so now we can have multiple variables point to the same spot. And if we didn't have this ability, it would be really impossible to code anything. So I had an example of it, but real quickly, you can imagine that we have 2 people. And somewhere else, we create a variable called logged in user. So there are buttons on Facebook that say change name. Change name is going to change the name of the logged in user. But the logged in user is going to be different every time we run the app or we log in and log out. And the login function is going to give a reference to whoever you are to be logged in user so that all the other functions know, hey, I'm going to whoever the currently logged in user is. If we weren't able to have references and basically pass these memory addresses to make sure that logged in user is going to change my name, and it's going to change what you see as friend number 1 and what you see as friend number 137, all pointing to the same spot in memory, it would be fucking impossible to get anything done. Because you would need a special copy of the program that has you as the logged in user. You would need another one that has you hard-coded in as the logged in user. And then we could never change that you're friend 37 for everybody and you're friend 100. Which means anytime we made a change to the social network, a programmer would have to hard code in these objects every single time. So references are really important. And so the main takeaway here is that when we're using these complex data types, we need to slow down and try to think about exactly what we're doing, and is the function mutable or is it immutable? Do we want it to be immutable? Do we want to still have the original array before we sort it or before we delete somebody from it? So we don't have to go all the way in depth where you write this out every single time, but certainly while you start, try to think about the scopes and try to think about, is this a reference or is it a value? And if I pass it this way, am I changing anything? Now, equality operators, how do complex data types evaluate their equality?
There's spots in memory.
Yeah, so variables that are complex data types evaluate whether they're both pointing to the same spot in memory. Now, arrays and slice. What does slice do in English? Deep or shallow copy? Shallow, which means that if we have a nested array, will the sliced version of the array and the original array that now hold that nested array, will they point to the same spot? They will. So if you change it in one, it's still going to show up in the other one that you thought you sliced and we're now safe from accidentally overriding. Any questions on that?
Can you, what was the thing you were just talking about for a deeper copy?
Okay, I'll send out a link to what Lodash is, which is basically a library. And when we leave this course and we're able to use the real world of JavaScript where we can just fucking install any library that hundreds and thousands of other people have already coded better than we can, it makes our life so much easier. And Lodash is a library that's filled with all sorts of functions that probably do a lot of the stuff we're making you do by hand in every single problem in this workshop.
Well, technically, every method could be coded by hand, but that's just torture, right?
Yeah, and you open up yourself to a lot more bugs. If I know that in this app I need to make a deep copy of something, and I start a new app next week, why am I going to sit there and figure out how to make a deep copy again? Just use the function I wrote last week. And that's why it's great that we should write things in functions that do specific things. We shouldn't just write a long set of instructions that's going to hand type out everything, because you never know what bit of code can be reusable. And so that's why functions should not have side effects. They shouldn't really touch the global window. I should be able to give you a function that just takes in an array, and it's going to give me back a deep clone version of that array. It's not going to touch anything else. It exists only on its own. So I'll link to what deep clone looks like in Lodash. I will link to a set of examples that shows how logged in user works inside of Facebook, and we can start the workshop. Sorry, this one's really long. It always goes this long. I really hope that it helps to slow down a bit and try to evaluate what's actually going on. And I'm glad that we saw a little bit more about how the order of operations works, how we need to evaluate this thing first, then evaluate this, then evaluate basically what this is, give that to the push method, and then this whole thing is what gets returned on that line. So we have to slow down and think about every little step, and that's really how you're going to build up your knowledge. So make sure you console log a lot. Console log your objects, check what they look like, check if you mutated the original one. Being intellectually curious is the best way to fill in the blanks that happened from this course moving so fast and throwing literally everything about JavaScript at you in 4 weeks. So it's perfectly okay to feel overwhelmed. Reach out if you need any help. Take a few minute break and we'll get started with the workshop, and I'll open up yesterday's solutions.